We are starting off this unit discussing momentum, in this case specifically linear momentum. Linear momentum occurs when more than one object collide, typically in a straight line. Momentum is labeled with the letter P and is determined by multiplying the mass of the object in question by the velocity at which it is traveling. Therefore, the units of momentum are kilograms times meters per second. A change in momentum occurs when an object changes its velocity. Remember, a change in something is represented by the Greek letter delta, and we find this by taking the final momentum and subtracting the initial momentum. We know that momentum is mass times velocity, so we take the final mass times the final velocity and subtract it from the first mass multiplied by the first velocity. The amount of force that it takes to change the momentum of an object is actually equal to the rate of change of momentum. So if we know the time it takes for a change in momentum to occur, we can determine the amount of force it takes to cause that change. We can write this simply as change in momentum over time. Typically, the mass of our system does not change. If we pull the mass out of the equation, we are left with a change in velocity over time, multiplied by the mass. Hopefully you recognize this as the expression for acceleration, and we also know that mass times acceleration is the force. So the rate of change of momentum is actually the mass times the acceleration, or the force. Let's look at an example. Calculate the momentum of a 110 kilogram football player running at 8 meters per second. We know the mass of the player to be 110 kilograms, and we know the velocity to be 8.00 meters per second. This works well because our formula for momentum is mass times velocity. When we plug in our numbers, we end up with a momentum of 880 kilograms times meters per second. We can do the same thing for the ball he is catching by substituting in the mass and the velocity of the ball. The mass of the ball is 0.41 kilograms, while the velocity is 25 meters per second. Finding the momentum of that ball, we multiply the mass times the velocity, and we get 10.3 kilograms times meters per second. If we compare those two momentums, we find that the momentum of the player is nearly 86 times that of the football. Even though the ball is traveling at a much faster velocity, its mass is much smaller, and it does not significantly affect the momentum of the player. We can turn this around and talk about this change in terms of the average force applied over a certain time and how the momentum changes. We call this change in momentum the impulse. Remember that force is the rate of change of momentum. The change in momentum is the final mass times the final velocity, subtracted from the initial mass times the initial velocity. If we divide that by time, it is the rate of change of momentum, which is equal to the force. The change in momentum, or the impulse, can then be equal to the force times the time. This gives us a unit for our impulse, and it works out to be newtons times seconds. We can relate this to Newton's second law and calculate the forces involved if we know how momentum changes over the course of a known time. In this example, we look at a tennis serve with a velocity of 58 meters per second. If the ball has a mass of 0.057 kilograms and is in contact with the racket for 5 milliseconds, what is the force applied to the ball? We know the change in momentum is equal to the change in velocity multiplied by the mass. In this case, we can assume we are talking about velocity in the horizontal direction, and that the ball has an initial velocity of 0 meters per second in the horizontal direction. Immediately following impact, however, the ball has a velocity of 58 meters per second. So our change in velocity is 58 minus 0. This gives us a change in momentum of 3.306 kilograms times meters per second. Force is the change in momentum over the change in time, so we divide our calculated momentum by 5 milliseconds. Keep in mind that milliseconds must be converted into seconds. To do this, we move our decimal places 3 times to the left. In the end, we get 660 newtons of force applied to the ball. If you imagine a car traveling at a certain velocity, hitting a brick wall, the car will come to rest upon hitting the brick wall very quickly. The mass will not change, but the velocity will become zero. The impulse will be the change in momentum, which is mass times the second velocity, subtracted from the mass times the first velocity. In this case, it ends up being negative mv1 because the final velocity is zero. That in turn equals the force times the time. If you imagine you are the driver of that car, the force that is applied to you will depend on the time it takes for the car to stop. If time involved in the stop is small, then the force is going to be large. You have probably been in some sort of sudden stop at some point and realized that hopefully your seatbelt applied a certain force to your body. If you can make that time longer, then the force applied to you will be less. Compare a sudden stop to a slower stop. You might not even notice the force during a slow stop to a stoplight. However, should you hit the brick wall, you will definitely feel the larger force. Cars are built with crumple zones that help to reduce the time a force is applied for just this reason.